We'd like to solve a couple of differential equations problems from beginning to end, starting with a Newton's law of cooling problem. Now, a metal object has been heated up to 700 degrees Fahrenheit, then placed in a constant temperature environment of 75 degrees. At that point, it's going to begin cooling, and it's going to begin cooling at a predictable level. In 20 minutes, the metal is cooled to 200 degrees. So what we need to do is first find a general equation that governs the temperature at any time, then figure out how hot is it after 40 minutes, okay? So if we start by letting T of T equal the temperature after T minutes, then that gives us the differential equation dt dt equals K times T minus 75, where 75 is the constant temperature and capital T is the temperature after any given time. Now, in order to solve this differential equations, we rearrange it and write it as follows. 1 over T minus 75 dt dt equals K. Now, if we integrate both sides with respect to little t, we have the integral of 1 over T minus 75 dt dt integrated with respect to t, which we know is just simply the same as this integrated with respect to big T, and then that equals the integral of K dt. Now with that, this equation here clearly is just the natural log, so we get the natural log of the absolute value of T minus 75 equals, on this side, we'd get KT plus arbitrary constant. And I'm going to call it C1 because there's going to be more than one. Now, because the temperature is hotter than 75 degrees at all times, we can drop the absolute value at this point. Now, when we exponentiate both sides, we do e to both sides, we have T minus 75 equals e to the KT plus C1, which is e to the KT e to the C1. And then that ultimately gives us T equals 75 plus, and we'll call e to the C1, let's call it C2. Since C1 can be any real number, now e to the C1 is some other arbitrary constant. And this, therefore, is the general form of the differential equation. Now we can easily solve for C2, so I'll go back up to here. We can easily solve for C2 because we know the temperature at time 0. At time 0, we started at 700 degrees. So we have T of 0 equals 700, which would equal 75 plus C2e to the 0. And with that, that means that C2 must be 625 in order to make this equation work. So now finally, we have something we can work with here. T of T is 75 plus 625e to the KT. This is our generic equation. Now, this isn't the end equation that we want because we still have to calculate the value of K. K is a specific constant that has everything to do with how fast this is cooling down. Now, a quick check. When T is 0, we'd have 75 plus 625 e to the 0, which is 700. And as T grows and grows and grows, this quantity should get smaller and smaller and smaller because it's cooling down eventually, meaning it's asymptotic to the 75-degree room temperature. That's a good sign. So now what we will do is we will take the one piece of information that in 20 minutes, we know the temperature, okay? So using this only, all right, in 20 minutes, we know that T of 20 is equal to 200, but that's equal to 75 plus 625 e to the k times 20, or I'll just write it as 20k. Now we have an equation where we can easily find k by using logarithms. So if I subtract 75 from both sides, I have 125 equals 625 e to the 20k. Multiplying both sides by 1 over 625 gives us 1/5 equals e to the 20k. Now, taking the natural log of both sides, I have natural log of 1/5 equals 20k, or finally, k equals 1/20th e, 1/20th natural log of 1/5. Now, that's not a very friendly quantity, but here's the beauty. We're going to insert this into here. And since k is part of the exponent, I'm eventually going to have e to the log. So here's how this is going to work. Let's go ahead and take that quantity right there. And we will insert it here. I'm going to have e raised to this. So my exponent is k times t. So if I take kt is 1/20th natural log of 1/5 times t. But remember the rules of logs. If I put the t here with the 1/20th, then I can take this and I can raise it up to the exponent. And this would become the natural log of 1/5 raised to the t over 20th power. And the reason why I want to write it in that form is it's now going to be e raised to this. And the e and the natural log will undo each other. And that will give us finally that t of t is 75 plus 625 times e raised to this, which is simply 1/5 to the t over 20th power, which is a much, much simpler formula to deal with. Do you notice we never actually did the calculation to find a decimal approximation for k, because k is a natural log and k is in the exponent. There is no logic to calculating k as a separate quantity when I can always do this process. You can always write e to the log in this context. So now this is the part we wanted. Okay, before I can ask you for 40 minutes, 50 minutes, 5 minutes, I need a general form now where the only unknown is time. So the final piece of the puzzle, t of 40 is 75 plus 625, 1/5 to the 40 over 20, which is just 1/5 squared. And if I run that through my calculator, that comes out to exactly 100 degrees Fahrenheit, which is beautiful. Now, it doesn't always come out as a nice number, but it did because I chose a multiple of the starting amount. So I basically was going to get an integer exponent by making that choice. Okay, so that's a lovely problem. Now let's do another one. We want to solve an actual differential equation. This one being an application, the next one's just a pure solve the differential equation type. And so the differential equation we're going to solve is one of the form y squared dx plus e to the x dy equals 0, okay? And I will have one initial condition, and that will be that y of 0 equals 1. That means when x is 0, y will be 1. Now, with that, I can't integrate anything yet because the variables don't match. So the first thing we're going to do is rearrange this. Now remember, dx and dy are not quantities. They are instructions. They tell me how I'm supposed to integrate. So I have to have x dx and a y with the dy. So the next thing we'll do is we'll multiply both sides by the reciprocals. I'm going to multiply both sides by 1 over y squared and by 1 over e to the x. So in this case, what that will give me on this side is negative e to the negative x dx equals y to the negative 2 dy. I just multiplied both sides by the reciprocals of these terms. Okay? Now I can integrate both sides. So quite simply, I'm making this my problem. Okay? That's all I have to do. Once I get it of the form function of x dx function of y dy, I can integrate. Dx and dy are not quantities. They can't show up in quotients, and they certainly can't show up in denominators. Now, when I integrate this one, that's just going to be e to the negative x. When I integrate this one, that's going to be negative y to the negative first plus c, or negative 1 over y plus c. I can solve for y, I can solve for x, I can put x and y together, but it probably makes sense to find the value of c at this point because I can substitute the initial conditions in. X is 0, y is 1. So at that point, I'm going to have e to the 0 equals negative 1 over 1 plus c, or 1 equals negative 1 plus c. That gives c equals positive 2. So now I've got, if you want to write this as 1 over e to the x equals negative 1 over y plus 2. If I put these together, this is an acceptable answer. But generally speaking, we'd rather solve for one of the variables. Preferably, we'd solve for the y variable. So I can rewrite that as 1 over y equals 2 minus e to the negative x, or I can write it as 1 over e to the x. Now, if I take the reciprocal of both sides, I've got y equals 1 over 2 minus 1 over e to the x. And at this point, the last thing I would do to make this a really nice quotient is I'd multiply top and bottom here by e to the x. So on my final answer, probably the best answer, probably the most useful answer, I'd have something of this form here. Now, what you have to understand is any form, this one included, this one, any form is legal. Any form is going to work as long as what you said is correct. But the most useful form is usually the one where you write y equals, if that is at all possible. So this is a standard differential equation. The Newton's method is a slightly different type of differential equation, but between the two, we're going to see probably the most important ones we'll look at.